Hello, today I would like to introduce to you a method to extend the mathematical theory. For example, assume that f is a function from the set of all real numbers to the set of all real numbers, and the function f is said to be even if this condition is satisfied. The condition says that if we take the value for negative x, then it is equal to f of x. And we also define f is odd if this condition is satisfied. So f of negative x becomes minus f of x. Then we can easily prove a theorem saying that when f is a function from the set of all real numbers to the set of all real numbers, then we may find two functions g and h whose domain is R and whose codomain is also the set of all real numbers, satisfying these three conditions. The first condition says that f of x becomes g of x plus h of x for all real numbers x, and g of negative x is equal to g of x, and h of minus x is the same with the negative h of x. We can prove this theorem as following. So we should find function g and h satisfying these three conditions. So actually we do not see whether the function g and h exists satisfying these three conditions, but we assume that there are two functions g and h satisfying the condition which is denoted by star. So this satisfied, then from the condition star we have these three conditions, and these three conditions should be combined well so that we can prove the theorem. So to interact the three given conditions, we replace x with negative of x from this equation. Then we can see that f of minus x is equal to g of minus x plus h of minus x. From this condition and this condition, by replacing this and this, we can get an equation given as f of minus x is equal to g of x minus h of x. Then by solving the equation given from the first condition and the second condition, we can easily take g of x in this way and h of x in this way. So actually, by adding the first equation and the second equation, we can see that twice of g of x is equal to fx plus f of minus x. So gx becomes f of x plus f of minus over 2, and hx can be given also in this way. And you can easily check that these three conditions are satisfied. Say that if we add g and h, then we can easily see that it becomes f of x, and g of minus x is equal to g of x, and h of minus x is equal to minus hx. So this is a basic theorem about an even function and odd function, and this can be similarly applied for the operation multiplication. So let's consider the set of all positive real numbers, which is denoted by r auto plus. And if f is a function from this to this, then we can easily prove the theorem that there exists g and h satisfying these three conditions for the reaction that the equation holds for x. actually you can see that plus is replaced with multiplication, and minus x becomes 1 over x in the first theorem in this condition. So we want to generalize the theorem, and we want to see the relationship with this theorem and group theory. Actually, we can take an example as following. If f is a polynomial function of degree 3 given in this way, then we can split f of x as the sum of minus 3 times of x squared plus 1 and twice x cubed plus 1. If we take this function as g of x and this function as h of x, then you can see that fx is given as the sum of g and h, and g is an even function and h is an odd function. So we have seen example of this theorem. Next, we consider a more complicated case. So let's consider the set S, which is given as the open interval. This can be expressed as the set of all real numbers which is greater than 1. And if f is a function from S to S, we want to show that these two G and H from the set of S to S are such that let's note the start the three conditions saying that FA equal GA HA minus G over A minus H over A plus 2, and A over A minus 1 is equal to G over A, and A over A minus 1 becomes H over A over HA over minus 1. Of course, we assume that the equality holds for S. So you can see that the problem seems to be much more complicated than this theorem and this result. So to prove this result, we start with some questions. So before we prove the result, the first step, we want to simplify the problem as following. And that first question is how to simplify the problem. So this equation seems to be a little bit complicated, and so the first step, we define new operation, define x star of y to be the multiplication of x and y minus x minus y plus 2, and And then we can see that, easily see that x star y is equal to y star x, and also we can see that x star 2 becomes x multiplied by 2 minus x minus 2 plus 2. This becomes x over x, and we can also see that x star x over x minus 1 is equal to x by the definition multiplied by x over x minus 1 minus x over x minus 1 plus 2, and so we can calculate it in this way: x squared minus x minus 1 minus x plus 2, and this becomes 2. So this equation holds for xy in s, and this holds for x in s. This way also holds for x in s. So in the first step, we can see that by using the star operation, we may simplify the given condition star as following. So the second question can be stated as follows. Question 2. We want to find G and H. The given condition star can be represented as Fa is equal to Ga star H of A, and Ga inverse is equal to Ga, where when we denote x inverse to be x over x minus 1 by using this notation, this can be simplified in this way, and we can also see that h of a to the negative 1 becomes inverse of h of a. So we have simplified the given condition star in this way. Then to interact these three conditions, we replace a with a to the negative 1, then f of a becomes J inverse star HA inverse, and by combining these three conditions, we can see that FA inverse becomes GA star HA to the inverse. Okay. So we have two equations saying that let's denote this equation by 1 and this equation by 2. So the first equation and the second equation should be interacted to get our result. So now we have a problem that solve FA equal GA star HA, and FA inverse becomes G of A star H of A inverse. How can we combine these two conditions? It is natural for us to multiply these two equations by using star operation. From this we can see that FA star FA inverse becomes by taking the star operation of the right hand side. We can see that this is equal to GA star GA, and this becomes by definition of star, this is equal to so we can get FA star inverse becomes GA square minus twice of GA plus 2, and by replacing GA with T square minus 2T plus 2 equal FA star FA inverse, where T is G of A. So we can, by solving this equation, we can see that G of A is equal to 1 plus minus square root of FA star FA inverse minus 1. So we find how to take G, and the third question is how to take H. We want to find HA. This can be obtained by the condition saying that FA is equal to GA star HA, and so we can see that HA becomes GA inverse star F of A, and in this way we can find H. So I have explained how to find G and H is defined the given condition locally, and this is not a proof. So let's see more in detail about the construction of G and H. So we define G can be given as this one, but if we consider the domain and range, we should take a plus, not minus, in this equation. So we define G of A to be 1 plus square root of FA star FA inverse minus 1, and HA to be inverse star F of then we should check that these three conditions are satisfied. So we should check that G GA star HA becomes f of A. So this condition is equivalent with this one. So we check this condition. Then by the definition of H, we can see that this is equal to GA star G of A to the negative 1 star F of A, and this becomes 2 star F of A, and this becomes F of A. And we can also see that G of A to the negative 1 becomes by the definition, and this is equal to 1 plus the square root of F of A star F A inverse, and so this is equal to G of A. And so we have checked that the first condition and this equation holds, and we should check this condition is satisfied. So let's see that HA inverse is equal to HA to the inverse. So this is equal to equivalent to show that by the definition of H, this is equal to GA inverse star of F of A equal I'm sorry, this is replaced with this one. This is equal to HA inverse. So GA star inverse, and you can see that this is equivalent to GA star G of A inverse is equal to FA star FA inverse. So you can easily see that this equation holds because this is equal to GA star GA, and by the definition of a star, this is equal to GA square minus twice of GA plus 2, and this is equal to, by the definition of G of A is given this way, then you can easily check that this is equal to FA star FA inverse. In this way, you can see that the result holds. Actually, you should note that the operation star is a very good operation, and so the star operation gives a group structure on the set of real numbers greater than 1, and this theory is very closely related with group theory. And so if you are interested in generalizing this result, then please group theory. Okay, thank you very much.